Okay, welcome everyone. It's a pleasure to introduce Bob Tarjan, someone who needs no introduction. Maybe I'll just say he's one of our most famous graduates at Stanford, since we're at Stanford. I'm teaching 161 this quarter, and Bob's name shows up very, very frequently. In fact, coincidentally, we just taught Dijkstra's algorithm yesterday. And so I told my students in class, here's the bonus for you. One of the legends of the field, Bob Tarjan, is going to be speaking about this very algorithm. And it's amazing that so many years after its discovery, we still have new things that we can find out about it. So without stealing the thunder from Bob, let me turn the stage to Bob.
Thank you. So I want to talk about our paper, which is called Universal Optimality of Dijkstra Beyond Worst Case Heaps. So we'll define universal optimality eventually for Dijkstra's algorithm. Co-authors are Bernhard Haeupler, who was a visiting master's student at Princeton with me, got his PhD from MIT, went to Carnegie Mellon, went to ETH in Zurich, where I reconnected with him a couple of years ago and started working with him and his undergrads and grad students and postdocs, Richard, Vashek, and Jacob. So there are 5 of us on this paper. So let's remind ourselves how Dijkstra's algorithm, I don't have slides for this, so this is going to be kind of informal, and there's not a lot of whiteboard here. You know, you need more whiteboards in this room. We'll see how this goes. So Dijkstra's algorithm is this famous algorithm which uses the greedy method to compute single source shortest paths. So we're given a directed graph with non-negative weights on the arcs, a distinguished source vertex, which I'll call S. We want to find the length of a shortest path from S to every other vertex, or potentially just to some subset of the vertices, or maybe even just a single target vertex, in which case we run this algorithm until we reach the target vertex. This algorithm is like breadth first search, but with weights. It's a greedy algorithm. We maintain a tentative distance for every vertex, which is the minimum length of a path found so far. We initialize the tentative distance to S to be 0, tentative distance for every other vertex to be infinity. And I'm also going to maintain a partition of the vertices into labeled, unlabeled, and scanned. The unlabeled vertices are the vertices for which we don't have any path yet. The labeled vertices are the ones for which we do have a path, but we don't know if we got the shortest path or not. And the scanned vertices are the ones for which we have the shortest distance. So initially, the source vertex is labeled. If all edge weights are non-negative, 0 is the best minimum distance to the source. The rest of them, we have no path whatsoever. The main loop is just, while there is some labeled vertex, we choose a labeled vertex with minimum tentative distance. And we know by the proof of correctness of this algorithm that this vertex, whatever this tentative distance is the correct shortest distance to this vertex. So we then scan it, we throw it into the scan set, we're done with it. And we scan it by looking at each outgoing arc and updating distances appropriately. So what does that mean? Let me say it this way. If some vertex W has not been reached yet, this gives us a first path to this vertex W. We'll set the distance, the tentative distance W, equal to the distance to V plus the length of the arc from V to W. So C of VW denotes the length or the cost of the arc, and I'm assuming that these are non-negative. And W now becomes a labeled vertex. It goes from the unlabeled set to the labeled set. Otherwise, if W is labeled and sorry, missing a crucial D of W is, sorry, is greater than, if we found a shorter path to W via V with this edge VW, then we want to do the appropriate update. So I should turn this around. If D of V plus C of VW is smaller than the current distance, we've got a better path to W going through V and taking the arc VW. We then do the appropriate update. And that's the algorithm. So to make this algorithm efficient, what do we have to do? We have to maintain the labeled set efficiently. And we've turned the graph problem here via this algorithm actually into a data structure problem, because the kind of data structure I need to keep track of the labeled vertices, Don would call it a priority queue. I will call it a heap. Store labeled set in, how about PQ? Okay, heap. So what are we doing here? This is a delete min operation. Find an item of minimum key, where the keys are the tentative distances in our heap, delete the minimum. This is an insertion into our heap. And this is a decrease key operation. We're decreasing the tentative distance of a vertex. The non-negativity of arc lengths guarantees that once a vertex becomes scanned, we're never going to find a shorter distance to it. So the progression of vertices is they start out unlabeled, they gradually move into the labeled set. When this step occurs, they move into the scanned set and they never get to be relabeled again. So every vertex is inserted exactly once, deleted exactly once, and then we've got some number of these decrease key operations. So this is going to be n. This is going to be n minus 1 if we start out with S already in the labeled set. And the number of decrease key operations is going to be at most something like m minus n, where I'm denoting n here as the number of vertices, and m is the number of arcs. Good. So Dijkstra's original implementation used a rudimentary implementation of the data structure here. He just stored the tentative distances in an array. An insertion takes constant time. Decrease key takes constant time because you just update the value in the array. But delete min takes linear time because you've got to scan through the whole array to find the minimum. So Dijkstra's original implementation is order n squared. Which is perfectly fine if your graph is dense, if the number of arcs is proportional to the square of the number of vertices. But the interesting, or an interesting setting, of course, is where the graph is large and sparse. So the number of arcs is more like the number of vertices than quadratic in the number of vertices. And the question is, can we reduce the time bound here, get it something close to linear in the edges? If you use a standard implementation of a heap where all the operations take log time, then you get order m log n. But if you can speed up the decrease key operations, you can do a little bit better than this. So back in the mid-1980s, Mike Fredman and I invented something called the Fibonacci heap, which takes constant time for decreased key operations and reduces the running time for Dijkstra's algorithm to order m plus n log n, which you'll notice is as good as this bound on dense graphs and as good as this bound on sparse graphs, and in between does better. So is this the end of the story? Dijkstra's algorithm is actually doing several things at once here. So it's computing true distances. It can be used to build or to find a shortest path tree. Which is a tree rooted at the start vertex such that all paths in the tree are shortest. And to augment the algorithm to compute the shortest path tree, every time we do an update here, we just keep track of the vertex V that gave us the arc into vertex W. And this set of arcs at the end becomes the set of arcs of the shortest path tree. And number 3, these vertices are coming out in non-decreasing order by distance. It sorts the vertices by true distance. And now the question is, can we say something more specific about Dijkstra's algorithm on any particular graph? This is some kind of absolute worst case bound on all graphs, but suppose we know something specific about the exact graph that we're considering. Can we beat Dijkstra's algorithm? Can we do better? That's kind of the universal optimality question. So I'm going to say that an algorithm for a graph problem with numbers in it like this problem, or let's just think about it for Dijkstra's algorithm. An algorithm is universally optimal if it minimizes the time or the comparisons on any given graph compared to the best possible algorithm on the graph. So to put it another way, I give you the graph. I don't give you the set of arc lengths. You can customize the algorithm based upon what the graph looks like. How fast can you solve these problems? Now we're going to concentrate on this problem in particular because it's the hardest of the 3. If you can sort the vertices by true distance, it's straightforward to build the shortest path tree, and you also get the true distances. So what we're going to prove is that essentially Dijkstra's algorithm with a slight tweak, well, Dijkstra's algorithm as it stands, if we plug in the right implementation for the data structure here, for the priority queue for the heap, it's universally optimal with respect to time. And if we tweak it a little bit, we can make it universally optimal with respect to comparisons, which means that even if you know the graph ahead of time, you can't customize your algorithm to do any better than this general purpose algorithm. Yes, please.
Graph is a can, even it does linear. The graph is just a chain.
Yes, then there's
So,
only
that's
one
why-
possible path.
Yeah, but Dijkstra is like still not good, even on the chain.
Well, if it's implemented using a standard kind of heap, I have to, that's an interesting special case. A chain, no comparisons needed. You got to spend linear time to output the answer. So you got to spend linear time, but no comparisons. So we're going to have to modify the algorithm to handle this case, among others. Yes, Don? Well, within constant factors. Okay. Yes. Uh,
Universal constant.
yes, the constant is independent of the graph. Good, yes.
Landscape. If we drop the requirement of 3, it's still open though to know the optimal.
Yes,
comparisons?
yes, and this is a very good question because there is an algorithm to find shortest paths on undirected graphs, which beats,
We publish the result on the for the FOCS for I think start yes. It was recently published. There is a work by me and some guys in Tsinghua University.
and what is the result?
So on the Professor Duan, he published the undirected graph.
Yes,
And we make the deterministic undirected graph.
Is it
So I
decreasing time or number of comparisons? Is it decreasing time or number of comparisons?
Yeah, it's comparison based and the running time is m not to the 2/3.
so it solves this problem, true distance problem, but it doesn't solve this problem.
Okay.
What we're going to prove is that this algorithm is optimal for this problem, sorting the vertices by true distance. So
I'm just trying to understand why our result stands and also it doesn't conflict with yours.
yes, I think it does not conflict, and that's because we're requiring the sorting here, and that's going to be critical to getting the lower bound. Because if you assume that you have to sort the vertices, we saw a sorting problem at lunch today, and there's a similar sorting problem built in here.
We have a single node and n nodes connected to it. Isn't that a sorting? Like a single node and n different nodes.
Yes, yes, then you have to sort.
Then that's, or you mean like on any graph? Okay.
Any graph, any graph. The claim is that this algorithm that I have yet to specify completely
Oh, no.
is optimum to within a constant factor on any graph, no matter what the graph is. So if it has to sort completely, it's going to sort completely. If it doesn't have to sort at all, it's not going to sort at all.
Like on that graph, Dijkstra sorts, but then you have to sort because you have to sort the node at 2 distance. So Dijkstra is optimal.
Yeah,
Whereas
because-
on the chain, you don't have to sort and Dijkstra doesn't sort either. So it's optimal either way. Okay.
Yes, that is the idea. Yeah, so the answer is this algorithm is not optimal for these problems, or at least for this problem. Okay, good. Any more questions? So let me define exactly what this problem is. I want to define, so I'm given a graph now. I've got some kind of fixed graph with unknown arc lengths. I'll define a distance order. This is equal to an order of the vertices by true distance. For some set of arc lengths. Right, so I don't know what the arc lengths are, but any possible distance order is a possible outcome to the sorting problem. So there's a lower bound now. If we define, let's say D equals the number of distance orders. Then we're going to have to use omega of log 2D comparisons and time to solve 3. Right, just by the decision theory argument, this is the standard sorting lower bound. So our goal now is to come up with an algorithm that will actually match this bound. We want running time, which is proportional to the graph size plus this, order m plus n plus log d time, and order log d comparisons. So in the path case, d is exactly 1. There's only one possible distance order. So this is going to be 0, no comparisons. To produce the output, we got to at least look at all the vertices. Actually, this is what we want here, m plus log d time, because in the path case, m is n minus 1. So we got to produce the output, we got to spend n time. Now, I'm not going to spend a lot of time dwelling on this. I want to spend more time on how we get to the log d here. And the answer is we need the right kind of a heap. And we almost saw the right kind of a heap this afternoon, a heap with the working set bound, except now we've got this extra decrease key operation that we have to implement. So unlike the sorting application, there was no data structure that achieved the right bound, including decrease key operations. So we had to invent one. So what are the steps going to be here? Everybody understands what the question is? So our task is to figure out the properties of the data structure, prove that if the data structure has the right characteristics, we're going to get a result something like this, and to invent the right kind of data structure and verify that it has the right properties. And just like in the sorting problem that I mentioned, or I talked about at noon today, in the original version of this thing, we get an additive in here in the number of comparisons, which we don't want. So there's an extra step we have to do to get rid of this additive in, because otherwise we're off on examples like this long path. All right, so let me list somewhere what we need to do here. We need to, 1, define the heap efficiency that we need, and that is the working set bound. And we need to prove that the working set bound implies order m plus log d time and order n plus log d comparisons. Maybe this is number 3 here. Number 2 is invent a heap with the working set bound. And number 4 is get rid of the extra, the plus n in comparisons. Comparisons. Those are the steps. Yes, question.
So in theory, you're comparing the elements, but here you're comparing some of the edge weights.
Yes, so our model is you're comparing linear functions of the edge weights, arbitrary linear functions of the edge weights. That counts as a comparison. Yes.
Would someone envision like a crazy algorithm that doesn't look based on comparisons? Maybe you just like, I don't know, compute the ratio of like 2 sums and like take the ceiling of it and look at that integer and do something.
We're assuming that the decisions are binary, that you're doing, and our model is you're doing comparisons of linear functions of the edge weights. So if you're doing something crazy, things might break here, yes.
What time it
You don't have to assume there are no ties because we're allowing arbitrary arc lengths. So the case of ties, that's kind of the easy case in a sense. In the lower bound constructions, you can assume that all the arc weights are different and sufficiently different that all these sums are different, so you don't get ties in the comparisons. There are technicalities in the lower bounds where you have to get rid of the ties, basically. I'm going to refer you to the paper for that part of it. If you allow nonlinear functions of the arc weights, for example, our proof doesn't work. The lower bound proof breaks. But that doesn't mean the result doesn't still hold. I don't know quite how you model the situation is the problem. Good. Any more questions? So the answer to 1 is the same thing that I said before. If we have an X that goes into our heap, here's the labeled set. X goes in and X comes out. We look at the elements that are accessed in between here, Y1 up to Y. Sorry, these are the items that are inserted. That is, they're labeled after X is inserted. The number of these, this is equal to the working set size of X. And what we want is that the time for a delete bin is the working set size, order log K time to do a delete min. Of X plus constant time for insert and decrease key. We'll say a heap has the working set bound if every deletion, the time required to do the deletion, is log of the working set size of the deleted element, and insertions and decrease key operations take constant time. Now, we didn't have decrease key operations at noon, So we can't rely on Iacono's result that says that pairing heaps have the working set property, because his proof didn't deal with the decreased key operation. So to do two, we had to invent a new data structure. There is a data structure that supports insert and decrease key in constant amortized time. And that's, for example, the Fibonacci heap, which is what gives this result. So our solution to number 2 was to use this in a 2-level data structure where we break the entire set of items into little pieces that are stored in approximately insertion order time, which allows us to get the working set size. So let me say just a bit about number 2 here. So the idea is going to be we have not a single heap, but some sequence of heaps. And each one of these is going to be can be a Fibonacci heap or anything such that we can do decrease key operations and insertions in constant time and delete mins in time proportional to the size of the heap. Standard efficient heap structure. And in terms of insertion time, these things are going to be ordered. Maybe I should do this the other way. The earliest inserted items are going to be in the biggest heap here. So if we look at a heap here, if it has some kind of size, let's call it size k, the time to do a delete min, if you're deleting something from this heap, is going to be order log k time. Now we want this to be the working set size of this. It turns out that you can allow these heaps to grow doubly exponentially in size, and the size of this heap is going to be enough to guarantee. This heap serves as the working set for any deletion out of this heap. That's what happens here. And I won't do the calculation for you. So then the game is we end up with a number of these heaps, which is something like log n, where n is the total. Well, I better use a different number, different letter here. Let's call this h. Total number of elements in all the heaps is little h. One of these is the minimum. We have to be able to keep track of the minimum, because what happens in a delete min, we go to the appropriate heap, delete its minimum. It's going to take log of the size to do it, but the working set size of all of these elements let's see, square root. If these are growing doubly exponentially in size, this one is going to be square root of the size of this one. All of these elements are in the working set size of every element of this one. So this has, if this has square root of the size of this one, and we take logs, that's enough elements to guarantee that the cost of deleting something out of here is log in the working set size of all of these elements. So if this thing is like k, this thing is going to be greater than or equal to square root k. And you take logarithms, and log of square root k is like 1/2 log of k. And these are all in the working set. So we're good. We got the working set bound. And when we're doing decrease key operations, they all stay within the same heap. So we got constant time for decrease key. And things always get inserted on the front end, and the heap here is constant size. So that's a constant time operation. We got a couple of headaches, though, because we have to keep track of which among this set of log n elements is the current minimum. And in order to maintain the set sizes, we have to occasionally combine two of these heaps together. So there's a merging process that happens here that we have to deal with. And we also have to deal with keeping track of the min of the tree roots. Every vertex is in exactly one of these heaps. Right. So there are some technical issues here. To handle the merging process, we use disjoint set union, which allows us to keep track of which, given an element, which heap it is in, because if we want to do a decrease key on an item, we have to know which heap is containing it. So this we use disjoint set union for. And those of you who know about disjoint set union will recall that this is not a constant time data structure. There's an inverse Ackermann function in here. But it turns out in this application, there are very few of these things, and they're growing in exponential size, and the inverse Ackermann function overhead goes away. So we end up with no problem here. And here, to keep track of the minimum, well, if the minimum is in one of these big heaps, we can afford to pay extra time locating it. So what we do is we maintain a suffix minimum. So for each node, we keep track of the smallest item to its right in this picture. So if we're at the root here, the root of the smallest tree, the suffix minimum is going to give us the global minimum. So that gives us a way to get a constant time to the item that we need to, the heap in which we need to do the decrease key. And then we have to worry about updating the suffix minimum when things change. But it turns out we can deal with all of that within the allowed time bounds, which are the working set bounds. So some technical details. I'll refer you to the paper for exactly how that works. To me, this is the least satisfactory part of this. This data structure is too ugly. There should be some better way to do this, but this was the best we could come up with so far. Prove that the working set bound gives the right time and comparison. So this is maybe the most interesting part. And let me see if I can say a bit about how this works. The original proof, so what are we trying to do? We're trying to somehow relate this working set bound, the time we're spending on the individual deletions, to the number of possible distance orders. And the original proof, which I did not develop, but my co-authors did, was rather ad hoc. But it turns out there's this beautiful lemma that does exactly the job. So let me try to state this lemma. This is relating working set bound to log d, the log of the number of distance orders. So let me state the lemma and then I'll explain how it works. Let's consider k subsets of the integers. This is actually going to be k intervals of the integers in the set 1 through k. Now this is the same k as that k. That is important. So these intervals are a1, b1, up to ak, bk. All right. Now we'll define a DAG on these intervals by the rule that AI, BI has an arc to AJ, BJ, AI, BI. If and only if BI is less than AJ. That is if these things are strictly ordered. So what do we got here? We got a set of intervals. Some of them are overlapping arbitrarily. But there's an arc between these two because this one stops before this one starts. There's an arc between these two. There's an arc between these two. And maybe that's it. Now we've seen DAGs and we've seen topological orders on DAGs, and we now want a theorem that relates the size of these intervals to the number of possible topological orders of this DAG. And here is the claim. This is a lemma. Let's let this DAG be I. T of I, this is the number of topological orders of the DAG. And the claim is that the sum of the lengths of the logs of the lengths of the intervals, I equals 1 to k, log of bi minus ai plus 1 is equal to O of log of ti. That is to say, the sum of the, so this is the length, the number of, if AI and BI are equal, this is 1. This is just the number of integers in each one of these intervals. The sum of the logs of the sizes of these intervals, you add up all the logs, and you get something which is at most a constant factor times the log of the number of total orders of this DAG that corresponds to these intervals. To put it another way, if you look at the product here, we get What does this constant factor do? It goes in the exponent. Actually, the constant factor here is essentially 1. What you can prove is that this is less than or equal to log of ti, 2 log of ti plus n, and you can throw away this plus n. But so if you look at the product, it's bounded by ti squared, something like that. And there's a beautiful probabilistic argument to prove this. I'll let you ponder it. But now we're just going to take this as a black box and plug in. So what does this have to do with working sets in Dijkstra's algorithm?
Above every choice of value, for every interval, we choose a value in that interval. The number of choices is the product of the interval sizes.
That's
And
basically the
somehow
argument.
corresponds.
There you go. Right. You sample from the intervals uniformly. You look at the number that give you a topological order. So it's a straightforward counting argument to prove this result. Thank you. Now the last step is we want to use this somehow. So how are we going to use this? So given a run of Dijkstra's algorithm, let W of X, or X in the vertex set, be the working set size of X. Then the sum of the logs of the working set sizes is equal to order log D. Where now this is the distance orders, right? This is log of the number of distance orders. This is the sum of the times of the delete min operations, assuming that we have the working set bound. So if this is true, this is telling us that the time to do all the deletions is within the allocation, which is some constant factor times log of the number of possible distance orders. So the proof is you just number these items in the order they get inserted into the heap. And then these intervals, the size of the intervals correspond exactly to the working set sizes. And every topological order of this DAG will give you a distance order. You need to prove that, but that's not too hard to do. And then this result follows immediately from this one. So that is the idea of the proof, that if you have working set bound, you're going to get the total time for all the deletions within the bound that you want. Now, what am I missing here? Where did the plus n go? There's a plus n in comparisons, and I'm a little mystified as to where it is, but let's get rid of the plus n in the comparisons by this kind of the same idea I used earlier today to get rid of this plus n in the sorting algorithm, which is the observation that if log d is really small, the extreme case being just a single path, you can't afford to have n comparisons. So we want to look at something like a longest path, but that doesn't exactly work. But what does work is this notion of a bottleneck, which I need to define a little bit differently here than I defined it at noon here. So step 4. Get rid of the plus n. Okay, so let me define the notion of a bottleneck. Let's suppose we do a breadth first search from, now I'm going to tell you something that's not in the original paper. This is a simplification of what is in the original paper. What is the observation here? There's this notion of a dominator. If I have the vertex S and there's some other vertex up here, V, such that in order to get to some vertex W, I have to go through V to get to W. We say that vertex V dominates vertex W. So if we know the shortest paths from V to all of these vertices, we can use that information to compute shortest paths from S, because we take the shortest path from S to V and then just add on the shortest path from V to W. So that's what we want to use here, but we don't have to consider the dominator notion in its fullest. All we have to do is look for a long path of dominating vertices. So we do a breadth first search from S. What happens? I'll draw S up here. This is ignoring arc lengths now. So this computation requires no comparisons. It just requires exploring the graph. These are now shortest distances. So the difference between the sorting problem and here is this layered graph, we got longest path lengths. Now we got shortest path lengths. So we got layer 2 and so on. Let's consider a layer where there's a single vertex. We'd call that a bottleneck. All right, so there may be several places where we get bottlenecks, and there's a lot of stuff in between. So each one of these vertices that's a bottleneck dominates everything down below. So we can break up this shortest path problem. We can treat this as a separate source, right? We can compute shortest paths from here down to here, shortest paths from here down to here, shortest paths from here down to here, and so on. Furthermore, for this to be small, there have to be many bottlenecks. There have to be constant fraction of the vertices that are bottlenecks. So what we do is we do a breadth first search. We figure out what the bottlenecks are. If there aren't too many, we can just run the algorithm as I presented it. If there are a lot, what we're going to do, there are 2 different solutions. I'm going to tell you the second solution, which I think is a little bit more elegant, which I kind of described, which is run Dijkstra's algorithm separately for each one of these pieces. So we start Dijkstra from S. We keep running it until the first bottleneck gets scanned. So we know the distance to the first bottleneck. Then we suspend the calculation here and we do a second Dijkstra. Start Dijkstra down here. We run this one until we get to the next bottleneck, and then we suspend and start a new Dijkstra down here and so on. So every time we hit a bottleneck, we're starting a new, you can think of it as a recursive Dijkstra with its own separate heap with the following proviso. There can be arcs that go backward, but there can never be arcs that go forward. So when we scan a vertex in one of these recursive Dijkstras and it updates a value in a previous one, we do the corresponding update. So the heap for this one is just sitting here, but we're doing decrease key operations. Eventually, we get down to the last bottleneck. Maybe this is the last bottleneck. This Dijkstra computation is going to finish. It's done. We back up to the previous one, finish that one, back up to the previous one, finish that one, and so on, all the way back up. And when you work out the details, that gets rid of this plus n. So in particular, with this long path situation, if you have two consecutive levels where there are consecutive bottlenecks, which has to happen a lot if you're in this bad situation, then the Dijkstra computation of the first one is trivial. You're not doing any comparisons because you're only putting one vertex into the heap and removing that vertex, and there's nothing to compare it against. So on a long path, if you run this recursive algorithm, you end up doing no comparisons whatsoever. And now I think I have described all parts of this. Yes, Don.
Where did Bernhard come from?
This is a breadth first search, right, in a directed graph. So arcs can only go forward one level, but they can go backward an arbitrary number of levels, right? Should I look at a specific example? Here's an example. Here's a bottleneck. Here's a bottleneck. I got backward arcs here. This is at level 0. These are at level 1, level 2, level 3, level 4. Because this could be the shortest path to this vertex. It could be that this is very long. This is very short. This is very short. The breadth first search is ignoring the distances. So even though this is long and hops, it could be the shortest path to this vertex. It's a little bit subtle what is going on here.
Then what? Do we have another update? Like maybe the voltage factory will be changed by a lot if you have a path going backward.
You're only scanning every vertex once. Every vertex is in exactly one of these recursive calls. So it only gets scanned once. So each of these edges only gets looked at once in the scanning phase. So if I'm down here scanning this vertex and I do a decrease key to update this value, I just go do the decrease key in the corresponding heap for this subproblem. And it just sits there until eventually I back up. I finish all of these recursive calls and I get back to this one. And now this becomes relevant when I'm doing the delete mins up here. These Dijkstras are nested, right? So the first phase of one of these is up until the time it scans the next bottleneck. Then the rest of the work gets postponed until everything down below gets visited and the shortest path values are assigned.
If it goes backward, we kind of just create another copy of it. And we just do it.
Well, there's no need to create another copy, because every vertex is only in one heap, and you can find it and do the update I mean, there are more complicated ways to do this, but this seems very straightforward. Questions? More questions? Yes.
What if you strengthen your definition of dynamic optimality by starting with balance on possible weights edge, perhaps corresponding to like weather conditions on the road?
I think that's a very good question. I don't have a good answer, although you could probably, if you could constrain, I mean, the key part of the bound, you got to do some work to prove that you actually have to look at essentially all the edges, right? That's the least interesting part, but if D were constrained based upon the arc weights, you could take that into account here, conceivably. Maybe, well, it would alter the lower bound. What happens with the algorithm, whether it's still optimal or not, I don't know. It might be an interesting question. Yes, Don.
I vaguely remember that Fibonacci heap had sort of a more complicated decrease key. It sort of decreased. You could say decrease all distances from that use this vertex as a domination or something.
Yes.
Was the original Fibonacci heap just supporting a single decrease key, decrease one key?
Yes, yes, yes. Yes, Moses.
Could one do something for minimum spanning tree? Some result of this kind?
Some of my collaborators have looked at that question so far without progress. I mean, the thing about minimum spanning trees is there's a randomized algorithm that runs in linear time, linear number of comparisons. You're sort of stuck with that, I think. So maybe it's not a meaningful question. There's a directed version of minimum spanning trees, the optimum branching problem, where maybe you could do something interesting. Actually, I asked that question of my colleagues. We don't have any results yet. But there is an embedded sorting problem, so maybe you could say something interesting. So what do you think? Is it truly linear for just computing true distances? What is your bound? It's like square root of log n or something.
All of it?
Yes, yes.
You want me to explain it? Kind of.
We're over time already. I'm curious what the bound is.
The bounding time is deterministic n times log two-thirds n. So m times log to the 2/3 n.
Log to the 2/3, not log to the square root.
So instead of m plus n log n, so let's say m is equal to n, then that will be n log n. But then in our algorithm, if m is equal to n, it will be n to the log to the 2/3.
Yeah, okay.
Yeah.
Very nice.
Near.
No, nothing rules out linear. What do you think? Linear?
Usually, we have like an obstacle that's like fail to log n. I think we'll probably get it fail to log n, but anything below that, it's kind of hard with building. But then I think log n will be obviously the next goal. So that will be, I'm not sure if you can do that in the future.
Wait, were you saying once it's below log n, it like snaps to log n because you reverse or something?
Yeah, I'm saying
I
that.
think that too optimistically.
Yeah. Like it's kind of like when you have a problem, then the best running time is like n to the 1.5. And you're saying that we want the linear. It's kind of analogous with that. So currently you have 2/3, and I think we think maybe like close and again will be possible, but then like maybe with some revolutionary idea we can get to knockout again. And obviously the ultimate goal will be linear, or maybe like another one. Yeah. Like this one.
Maybe we should take.
We're not asking direct questions.
Maybe
Thank you for the very nice talk.
maybe we should
Yeah,
thank
thank you.
both.
Yes, yes.
Yeah,
All right.
if I know your ideas earlier, we would have. Oh, you would make my thinking way easier. We would have known about what not to think about.
Yeah,
Well, let's thank both for listening, talk.
thank you.